So this is a title, AI4Medicine and Medicine2AI. So a lot of numbers, because that's what I do. I do statistics. I do machine learning, this type of thing. So for this event, I just kind of summarize my research into 3 kind of buckets. The first one is predictive modeling. So you give me some input. It could be very complicated, like images, curves, so that should be okay. And we want to predict something like mortality, patient's disease status, things like that. And we can, so the second bucket is interpretable machine learning, which is very important, particularly for medicine. Third one is uncertainty quantification. So the first one is, well, we want to be able to handle many different model of data, like images and brain connectivity, things like that. So those are some images we are able to deal with so far in my group, like a PET image scan, brain scan, and the blue matrix, that's brain connectivity, like how connectivity can inform, like maybe how smart people are, or maybe disease trajectory. And then we have some eyes or images from astronomy, and also some curves. In many data, you do have curves. So what we want to do is to go from those very complex data to predict something that is clinically relevant. So those are some kind of recent examples we have, like in terms of publication. So we use time series data, and the setting is ICU. We are able to predict like a disease called AKI, acute kidney disease, and we are able to achieve high accuracy, things like that. And we also do images and ensemble learning. So, and this is like just predictive modeling, and the accuracy is kind of very important. But accuracy is kind of the starting point, actually. So another example is closely related to the collaboration with the Methodist folks. So on my right, you see the echo images, and on the right, you see CMR. And we want to go from echo to CMR. So because echo is widely accessible, it's cheap, and it's good. And CMR takes time, but it's accurate sometimes. So let's use that as a gold standard. This is only possible for when you have data, like for the same patient, you do have the same modality, right? And we are so fortunate to have data from our Methodist collaborator, like Ashley Skuha is here, as wonderful in the audience, and Sadir earlier gave a talk. So so we pick one kind of outcome to demonstrate the usefulness of this approach. Here we pick a right ventricle, but it could be something else, right? So you want to predict RV dysfunction, which is based on CMR. You have some assessment, and we want to use echo to predict that, right? Echo is noisy, but you have a lot of echo images, right? So, and the goal is to go from echo to CMR to fill up the gap. And so you would think, you give me the data, I will give you the result the next day, but no, the data is super noisy, and we need to go through millions of steps, right? Like those steps, you don't know them, so it's kind of very complicated. We do all them, and then we go from the raw image, we have some kind of processed data, like in curves, tabular data, so it's much cleaner right now. And then we use the processed data to do the prediction. So this is an AUC we are able to achieve for this particular endpoint. And then we also use some machine learning technique, so that's what we do. Basically, we train a transformer here. But high accuracy is kind of the starting point, right? And we hope to add some understanding to the whole pipeline, particularly for high-stake field like medicine. So you want to make sure your model is interpretable, and when things do not work, you know what went wrong. Okay, so interpretable machine learning. So from the box on my right, so you have the interpretability. You hope to have a simple model, understandable, tangible, and very easy to debug, to monitor. So everything's good with this interpretable model, but maybe the accuracy is not the best. So on the next one, you have flexibility, like deep learning, those type of neural net, very flexible, and you have a high accuracy. So you want to kind of have borrow the best from both worlds, right? And so there are many kind of things you can do in order to achieve a balance. What we do here is symbolic regression. So symbolic regression is a very useful tool to give you nonlinear dependence while achieving those kind of high accuracy and also interpretability. So a well-known example is BMI. So you know BMI is a formula. That's a symbolic expression. You know how to interpret that. You can write down the formula, right? What we do is to give us massive data, we are able to find formulas like this, highly predictive and you know what's going on. So it's not a black box, it's very transparent, and you can do debug, but it's also highly accurate, right? So we apply this type of technique not only for medical application, but also for material science. So for material science, sometimes to kind of engineer a new material is very hard, and you're better off, you know, some kind of magic formula you can use to replace complicated physical laws. So we do that for catalyst design, and so those are kind of a line of work we have to add in this interpretability to the pipeline. But they are more than symbolic regression. So in risk, in medical practice, probably you want some integer coefficients. So you would have integer scoring system. So for questionnaire, you can score a patient based on different biomarkers. So you want this kind of scoring, and we can do that. And we also do dynamic risk scoring and identify biomarkers, but with very careful error rate control, like false discovery rate control. So we want to be kind of responsible. And we also use LM, large language model, to aid those kind of interpretable modeling so that you have flexibility, but you also emphasize the interpretability. So those are a few other examples along this line, like a causal inference. So this clearly is not, like prediction is important, but maybe causality is also relevant. So when that's the case, we need to bring in this interpretability into the game. So another example is also with Methodist collaborator, so Meng and Deepan, and we are able to use machine learning to identify a new cluster, a phenotype. And so that is highly interpretable, and we need to rely on collaboration with clinicians to make sure really this makes sense. So we are using machine learning to find it, and it turns out to be kind of reasonably practical and interpretable. So we have this JACC imaging paper talking about that. All right. And then the next level is like when we kind of keep growing. The next level is uncertainty quantification. So, and you give me a prediction, give me an estimation, but can you talk about the uncertainty? Like, how about the generalizability of the approach you have, right? So there are a couple of things we can do, like I just give a few examples, like post-selection inference. So you use a data set to select a relevant biomarker, and you use the same data set to make inference, right? This is double dipping. And there is some issue. And actually, another issue is false discovery rate control, which is related to reproducibility crisis, right? Whether your study is actually reproducible. So we want to be responsible in that regard. Like informal prediction, so give me an interval instead of a point estimate, right? We can also do fast approximate Bayesian inference, which give you uncertainty, but with a theoretical guarantee. Right? So for this type of work, actually, this is more like the world I live in. You need to do math. You need to mathematically show the uncertainty quantification you provide is trustable. Trustworthiness is like a crucial in this type of work. Like you see this very fun stuff. All right, to summarize, so today we very briefly go over predictive modeling and interpretable machine learning and also uncertainty quantification. We apply all of them to medical problem, to the wonderful data sets produced by our Methodist collaborators, like image data, time series data, or even tabular data, traditional tabular data. We are able to have new finding, have accurate prediction, and also give you some new biomarker. So yeah, this is great. This is AI for medicine, right? But during this journey, the medical application is actually a very strong motivation to motivate new machine learning research. Like along this line, we are able to develop a new symbolic regression technique, like a peak detection, because sometimes in curve, you want to detect the peaks. And also so if you have a curve, you do functional data analysis. Can you develop a new functional data analysis technique broadly applicable for any curves you might have, right? So those research are actually clearly motivated by the collaboration we have in this medical domain. So in turn, actually, medical research can motivate our new methodological development, and we have new tools. So now you have a loop. So it's a very healthy, organic loop. It's a loving loop. So this loop is impossible without the collaboration between those two institutions. I want to emphasize, so any collaboration, based on my personal experience, is not that easy. So it may sound like easy once the paper is done, you know, why it's not too complicated, right? But actually, it's a long journey. Like so the data set might take 6 months or even a year to collect, right? And then once you give me the data set, always there some issue in order to apply off-the-shelf method. You always need to do something, right? So it's kind of it's a dirty, but in a intelligently challenging way. So, and this loop kind of motivate each other. I believe, I really look forward to have this kind of institutes between the two institutions, and we join effort and share expertise and motivate both medical research as well as AI research, right? So clearly, Methodist is leading like many fields you do, right? And Rice, we do AI, we do many other stuff, like wonderful kind of devices thing. And if you listen to the talk, so really wonderful stuff. We can join efforts and advance both fields. So with that, thank you very much. This is my email. I look forward to connecting with you here and offline. Thank you.